Just dialing in, we're talking about how well he's serving at 6 East.
30, 15.
What if I told you that winning a tennis point about 70% of the time can make you win the entire service game more than 90% of the time? That sounds like probability is giving the server extra credit, but it is not magic. It is the structure of tennis scoring. Winning a point is not the same thing as winning a game. So where does the extra probability come from? To understand the jump, we first calculate the chance of winning one service point. A serve point has two main routes. The first serve goes in and the server wins after that first serve. Or the first serve misses, the second serve goes in and the server wins after the second serve. The first serve lands in 71.2% of the time. He wins 76.8% of those points. When the first serve misses, we assume the second serve lands in and he wins 54.8% of those points. Multiplying along the branches and adding the roots gives about 0.7046. So the server wins a single point about 70.4% of the time. Now we model each point as a Bernoulli trial. The random variable x sub I is 1 if the server wins the point and 0 if the server loses it. The running sum counts server points across the game. The model is simple on purpose. It treats each point as independent with the same win probability p. Real tennis has momentum, fatigue, and tactics, but this clean model already explains a surprising amount. Before deuce, there are three ways the server can win quickly. A love game, 4-0, has probability p to the fourth. A 4-1 game must end with a server point. The first 4 points contain exactly 3 server wins and 1 receiver win, so there are 4 paths. That gives 4p to the fourth times 1 minus p. A 4-2 game also ends with a server point. In the first 5 points, the server needs 3 wins and the receiver needs 2. There are 10 in either order and return to deuce. That loop is the key. If q is the probability of eventually winning from deuce, then q equals p squared plus 2p times 1 minus p times q. Solving the recursion gives q equals p squared divided by p squared plus 1 minus p squared. Now we assemble the game. The server can win 4-0, 4-1 or 4-2. Or the game reaches deuce at 3-3 after 6 points, and from there the server wins with the deuce probability. That gives the full formula for g of p. When p equals 0.704, g of p is about 0.906. A 70.4% point edge compounds into a 90.6% game edge. The graph shows why this feels so dramatic. The dashed line is what would happen if game probability simply equaled point probability. But tennis scoring bends the curve. At 50%, nothing is amplified. The game is still 50-50. At 60%, the server is already much more likely than 60% to hold. And near 70%, the curve climbs into the 90% range. Small advantages do not stay small when the scoring system rewards repeated success. Now compare the model with the Zverev serving example. Using first serve percentage, first serve points 1 and second serve points 1, the estimated point win probability is about 70.4%. The theoretical service game win probability is about 90.6%. The actual service game win percentage is about 90.2%. The simple model is not perfect, but it lands remarkably close. So the story is this: tennis points can be modeled as Bernoulli trials. Tennis games are non-linear probability machines. Deuce creates recursion, and small point level advantages become huge game level advantages. So sports analytics is probability wearing sneakers. Thank you so much for watching. Please subscribe to my channel for new upcoming sports mathematics videos.